Hello everyone, this is Ksenia Larshna. I am the tutor for Trio Journey. Today we'll be going over oxidation numbers, redox reactions, and HalfCell reactions. So for oxidation numbers and rules for assigning them, the first one is the sum of the oxidation number will always be equal to the particle's charge, meaning that in this case for the carbonate polyanion, as you'll see that in some cases, in all cases for oxidation numbers, the oxygen is always -2, unless you're trying to find it. So here, we're going to try and find the carbon oxidation number. So since we have one carbon, we're trying to add and find its oxidation number. So add 3, -2, because this is the oxidation number for oxygen. And we know, and we know our charge is -2. So we set it to -2. So this would equal to -6. Add 6 to this because trying to get our carbon on its own. So our carbon is equal to 4, +4 for its oxidation number. Now we're going to try and find manganese. So we have 1 manganese plus 4 oxygens. Let's just erase this. And it's equal to -1. So this equals to -8. So we're going to try and add 8 to the other side to get manganese on its own. So Mn equals 7, because 8 subtract 1 equals 7. Now let's try and find chromate. So we have 2 chromates in this case. So 2 Cr plus 7, because we have 7 oxygens, 7 -2 equals -2 for its charge. So this would equal to -14. So add 14 to both sides. And then we have 12. And then we have to divide 2 in order to get our chromate oxidation number, which equals to +6. So our chromate equals +6. The second rule for oxidation numbers is that the neutral atoms are always 0. So if we have, let's say, silver, that's solid, its oxidation will always be 0. Unless it clearly states that it's 2+, then its oxidation number would be 2+. The same as for oxygen. It has no charge, so this is a neutral atom, and it's diatomic, but it would be 0. So oxidation number for a non-VOS metal depends on their group. VOS metals are variable oxidation state metals, meaning their charge can't be found based on their anion. Based on the periodic table, sorry. So VOS metals are usually your transitional metals, these, unless it clearly states that, like in aluminum, it's a 3+, and Ag is 2+, Yeah. Okay. These are your anyways. So next, oxidation numbers for VUS metals are found based on their anion. Oh, sorry. For 3 oxidation numbers for non-VUS metals depend on their group. So for group 1, they're always +1, and then group 2 are always +2. So these never change. It's only the transitional metals that you'd have to worry about finding their oxidation numbers for. Oxygen is always -2 unless you are given a hydrogen, which is always +1, and then fluorine is always -1. And chlorine is usually -1, but unless it's next to a fluorine or an oxygen. So typically we would find the chlorine in that case. And if we don't have any any of these 4 elements, then we always go by the more electronegative one, or the one that's closest to fluorine. So if it was, let's say, sulfur versus selenium, we'd go with sulfur's charge, which in that case would be a 7 negative. Oh wait, a 2 negative as well. And this one would have been 2 negative also, unless it was bromine. But in that case, because sulfur is closer to fluorine than bromine, it would be a 2 negative instead of a negative. And be looking for bromine instead of sulfur. So the last rule is oxidation number for nonmetals are typically found based on their group. So we just discussed that. The ones that we always assume are fluorine is always -1. And then hydrogen is always +1. And if we are given either fluorine or hydrogen, then we go by oxygen, which is a -2. Okay, let's do some redox reactions. So an example of a redox reaction is C copper solid +2 silver +1 charges going into copper cation, aqueous, this would be aqueous as well, and 2 silver solid. So as we've learned before, the oxidation numbers for these, since this is a neutral atom, this would be, its oxidation number would be 0. Oxidation number also doesn't rely on the coefficients here, unless the coefficient was a subscript. So in this case, this would just be a +1. We don't multiply the +1. So, and then our copper here, its oxidation number is a 2+, because that's its charge. And then this is also a neutral atom, so it's also 0. So you guys probably heard of this, but there are 2 mnemonics, GER and LEO. GER is gain electron reduced. And Leo is lose, electron, oxidized. So because the copper increases in charge here to here, it loses electrons to become more positive. So this is oxidized. The silver here, oops, gains electrons in order to become 0 or more negative. So this is it gained electrons and it's now reduced. Okay. Another example would be CrO7 negative plus IO negative aqueous going into O3 negative aqueous plus Cr3 plus aqueous. So the oxidation numbers for these are, these you'd have to calculate, but this comes out to be the Cr equals +6. This becomes +1. The IO3 negative is +5. The Cr3 plus is 3 plus because that is its charge. So the way we got these are we multiplied 1 Cr plus 7, because that's our amount of oxygens, equals to -2. This equals to -14. Add 14 to both sides. No, wait, this is 2 Cr, sorry. And 2 Cr equals 12. Divide by 2, and Cr equals +6. And IO we find because 1I plus 1, -2 for the oxygen equals -1. This equals to -2. Add 2. And I equals +1. And the same is for IO3 negative. So I plus 3 if 2 -1. This equals to -6 plus I -1. Add 5. And I equals +4. Wait. Sorry. +6 and equals +5. And this is 3 plus because that's the charge on that cation. That's how you find your oxidation numbers. And so here, the IO lost electrons, so Leo. And O stands for oxidized, so this is oxidized. Cr, gained electrons because it went from +6 to 3 +3. So we gained 3 more electrons. So we now, since we gained electrons, we're now reduced. Okay, now to solve for half-cell reactions. So writing out oxidation and reduction on half-cells. So So the oxidation numbers for these are 2 plus, +7, 3 plus, and +2. So this is reduced because it gained electrons. And this is oxidized because it lost electrons. So next you'd want to separate your reaction into half cells, meaning you would separate your oxidized into their own reaction and your reduced into their own reaction. So this would be your oxidized reaction. And reduced reaction. So that would mean your oxidized would be Fe 2 plus aqueous going into Fe 3 plus aqueous. And then your reduced reaction would be Mn, MnO 4 negative aqueous going into Mn 2 plus aqueous. So you would then balance your half cells by mass. First, balance elements other than hydrogen and oxygen, meaning you would balance your iron into iron. So you have 1 mole of iron here in the Fe2 plus, and then you have 1 mole of iron on your Fe3 plus. So that's already balanced. And in your reduced reaction, you have the 1 mole of manganese and the 1 mole manganese on your product side. So then you would add water to where oxygen is needed. So in your oxidized reaction, you don't need to add water because there is no oxygen. And in your reduced reaction, you have oxygen right here. So you would have to add enough water to balance out the oxygen on your reactant side. So let's just rewrite that again. So reduced. So Mn for negative aqueous going into Mn2 plus aqueous. And we're going to add 4 waters because we have 4 oxygens. Don't forget about your subscripts. Now we've balanced out the oxygens. Then you add H plus where H is needed. Now that we've balanced out our oxygens, we now have 4 times 2, meaning 8 oxygens, 8 hydrogens we need. So we have 8 hydrogens on our product side. We need to add another 8 hydrogens on this side. So that would be the H plus, which would be protons in this case. So I'll rewrite this equation. So now we balance our half cells by charge by adding electrons. So on this side, we have 8 hydrogen protons and 1 negative. So 8 plus, add 1 negative equals 7 plus. And on this side, we have 2 plus. So we need to add enough electrons to have 2 plus on both sides, because that's our least number. So we could add 5 electrons on this side. And then on our oxidized reaction, we have Fe2 plus into Fe3 plus. So we would need to, since we have a 2 plus here and a 3 plus here, we would need to add 1 more electron on this side in order to balance out this, meaning add 1 electron equals 2 plus. So they're equal charges on both sides. So now that we have done that, we have now Fe2 plus Fe3 plus electron, and then MnO4 negative plus 8H plus going into N2 plus aqueous plus 4H2O and 5 electrons. So now we would multiply our reactions to add them together, and by their least common multiple. We have 1 electron on our iron, and we have 5 on our manganese side. So we would multiply this by 5. So we would now have 5 Fe2 plus Fe going into Fe3 plus and adding 5 electrons. Another way you can find out if you're doing this right is if your electrons cancel out once you add them together. So one way you can see is if the electrons are on opposite sides on the equations. So on our product side, we have our 5 electrons, but on our manganese, we have our 5 electrons on our reactant side. So now you put your half cells together. So we have 5 electrons plus MnO4 negative plus 8H plus adding our 5 iron plus going into Mn2 plus adding our 4 oxygen water, adding 5 iron 3 plus, and 5 electrons. This is the part where we cancel out our electrons, because now they're balanced. And then we count and check if we have everything in order and we have everything in the correct spots. And if this is a basic solution, you're going to add hydroxide. So add 8 hydroxide. We have 8 H pluses that we need to neutralize. And if you do something on one side, you have to do it on the other side because this is a balanced equation. So this would turn into 8 H2O because hydrogen and hydroxide turn into water. And that would mean that these 4 waters would cancel out. So you just subtract 4 waters from each side. And that's gone now. So now you would have MnO4 negative plus 4 H2O plus 5 iron 2 plus going into Mn2 plus and 5 Fe3 plus and 8 hydroxide. And this is if it's in a basic solution, but if it is in an acidic solution, keep it as it was before without adding the hydroxide. Okay. And another example is this. So we would first want to get our oxidation numbers like before. Here we have 8 plus 1, negative 2 for our oxygen. Cr is a plus 3. Our hydroxide is negative 1. Cr here is plus 6 and negative 2 for oxygen. Cl is a negative 1 because that is its charge. So here our Cl, our chlorines are reduced. They gained electrons. And our Cr had lost electrons. So now there you are, they are oxidized. So next, like prior, we write them out into their own separate reactions. So we could write Cl. This is our reduced reaction. And then our oxidized reaction, so Cr. So, do that soon. So you would add water to balance out the amount of oxygens you have, and on this side we have 1 oxygen. So add 1 H2O. Here do the same. So here we have 4 oxygens. Don't forget your subscripts. So we add 4 oxygen, 4 waters. Balance that out. So, because we have 4 hydrogens, we want to get, no, that's because we have water. And then you're going to multiply add our hydrogens in order to balance them out. So add 2 H plus because we have 2 waters. And then add 6 H plus. Okay, so wrong. This is adding 4 H plus because we have 4 H's on that side, but we have our 4 oxygens. Sorry, that's my mistake. Then we add our electrons. Wait, that was right. Add our electrons to balance them out. So here we have 2 electrons because we need to add them in order to have our correct number. And then for this one, we add 3 electrons. So now we multiply by our least common multiple. So we have 3 electrons on this reaction. So we will multiply this by 3. And we will multiply our bottom reaction by 2 because our electrons there are 2 electrons on that reaction. So here we have 6H plus 3 O negative plus 6 electrons going into 3Cl negative plus 3H2O. Here we have 2CrOH, 4 negative, 2CrO4, 2 negative plus 8H plus and 6. And 6 electrons. So now we add these reactions together. And we have 6H plus 3Cl negative, 6 electrons plus 2CrO4 negative going into 3Cl negative plus 3H2O plus 2CrOH2 negative, 8H plus and 6 electrons. Cancel out your electrons. And now you are going to get rid of your hydrogens where they're the least amount. So here you have 6 and here you have 8. So subtract 6 H pluses. And now you have 2 H plus here. So now your reaction would be 3ClO negative plus 2Cr, 4 negative, going into 3Cl negative plus 3H2O plus 2CrO, H2 negative, plus 2H plus. And if this would be completely okay if this is in an acidic solution, but if this is in a basic solution, you are going to add hydroxide. So you'd add 2 hydroxide, and if you do that to one side, you have to do that to the other side. And this would turn into ultimately 2H2O. So now you would have 3ClO negative plus 2CrOH, or negative going into 3Cl negative plus 5 because of these waters plus 3. That'd be 5H2O plus 2CrO4, 2 negative. And that would be if it's in a basic solution. I hope this has helped you, and have a great day.